So in this video, we're going to be looking at differentials. So you probably do know what a differential is if you've done differentiation, but you just don't know that you know it. So let's just look at what it is. So you probably know the Leibniz notation dy dx, right? You've used this before. And this notation is equivalent to y prime. This is the same thing. This would be Leibniz notation, and this would be Newton's notation. Now, let's try to understand what this means. What does dy by dx mean? So dy by dx is basically the differential of y over the differential of x. What does the differential of y mean? Well, the differential of y, if we just look at dy, it's a change in y that is infinitesimally small. So dy is a change in y, so it's a change in y that is infinitely small. Change in y infinitely, I cannot spell, infinitely small. Hopefully I spelled this right. And dx is a change in x that is infinitely small. Infinitely small. Now, dy by dx is basically a change in y that's infinitely small over a change in x that's infinitely small. What does that mean? Well, you probably know the slope formula. The slope of a line is equal to delta y over delta x. This looks a lot like delta y over delta x, doesn't it? Well, that's because it kind of is. Delta y over delta x is for a slope of a line that has 2 points, right? We've seen this before as y2 minus y1 over x2 minus x1, or we can also do y1 minus y2 over x1 minus x2. This is because we have 2 points. Now, when we look at dy dx, we're looking at the slope, we're looking at the derivative, which is the slope of a tangent line. We have only 1 point. And when we have only 1 point, our change in y is not going to be a finite number, it's going to be an infinitely small number. So it's going to be a small change in the y direction, small change in the x direction, and small change in the y direction. So dy dx. Now, this is just me drawing it, but that's not going to be the case. It's infinitely small, so it's not going to be a finite number. Now, the thing with differentials, though, is that we can use differentials to approximate the change in y or the change in x for a function. So let me give you an example. So let's say that we wanted to find the change in y for a function that has dx equal to 0.05 and x equal to 4, and the function is f of x, which is equal to 2x squared, for example. Okay, so this is interesting, right? Find the change in y for a function that has dx is equal to 0.05 and x is equal to 4. And then we have f of x is equal to 2x squared. Now, you might be wondering, well, dx is infinitely small. Well, we can actually just kind of fix this, or kind of do this, do something that wouldn't necessarily be the proper notation, the proper way of doing it, but we can do this and we can use it as an approximation. So dy, if we multiply by dx on both sides, we'll just get y prime dx. dy equals y prime dx. So by doing this, what we can do is we can approximate the change in y for a change in x. Now, dx in this case is a finite number, but that's not going to be the case. But we can do this just for an approximation. So find the change in y for a function that has dx. I should just say find dy for a function that has dx of this, x equals 4, and then f of x equals 2x squared. So from x equals 4, and then we're looking at 4.05, and then the change in the y. We could have obviously just plugged 4 in and then found the y, and then plugged 4.05 in and then found the y, and then took the difference between the two. But that's obviously going to take a little bit more time, so we can use the differential equation as well. So let's do that. So dy is going to be equal to, what's y prime? What's the derivative of this? That's just going to be 4x. and then dx, which is multiplied by 0.05. Now x is 4, so that's just going to be dy is equal to 16 times 0.05. So 0.05 is also equal to 5/100ths, which is going to be equal to 1/20th, right? 1 by 20. So let's do that. It's just going to be 1 by 20. 1 by 20, which is just equal to 16 by 20. 16 by 20. Both are divisible by 4, so it's just going to be 4/5, right? 4/5. Now this is going to be what we have as our change in y. Now let's look at the actual change in y. So 2 times 4 squared is equal to 16 times 2 is 32, and 2 times 4.05 squared is equal to what? So this is a hassle, right? We have to square 4.05. I'm just going to use a calculator. This is why we kind of use an approximation. So 4.05 times 4.05 is going to be equal to 16.4025, and then multiply this by 2. 32.805. 32.805. Notice that the difference is going to be, so take the difference of this minus the difference of this, or minus this number, is going to be 0.005. So that's going to be, this is 0.8, so it's going to be roughly equal to each other. Now the thing is, this was easy to evaluate. You can just plug in 4, you can plug in 4.05, but let's say that we had a function like f of x is equal to the square root of x, or something like this. Now if we wanted to look at the change in y from, like, if dx was equal to 0.05 and x was equal to 4 in this case, then the square root of 4 is easy. That's just going to be 2, but dx is 0.05, so that we need the square root of 4.05, which that's not going to be very easy to do. So we obviously will know it's between 2 and 3, but it's not going to be an exact number, and we're going to have a hard time finding this. So that's when we use differentials to approximate this. So differentials can tell us delta y, dy, and that can help us identify the change in y for a change in x. Now, another thing that I wanted to point out is that since dy by dx is exactly equal to y prime, delta y by delta x is an approximation of y prime. This is not the derivative. Just like the slope of a secant line is approximately equal to the slope of the tangent line, but keep in mind that is when the points are close to the point of tangency. This is just an approximation, since delta y is going to be a finite number, and this is supposed to be an infinitely small number. So delta y by delta x is going to be an approximation for y prime. So if we plug in delta x, it's going to be an approximation, but as it gets smaller and smaller, as the distance gets smaller and smaller, if you've looked at a average rate of change and secant line, as it gets closer and closer to the tangent line, the point of tangency, it gets better and better of an approximation. The slope gets better and better. So as delta x gets smaller and smaller and delta y gets smaller and smaller, we have a better approximation. So this is more and more accurate. So that means that if dx is even smaller, we're going to get a better approximation. So let's try that. So let's say we had the same function up here. So we're just going to have x equals to 4, and this kind of dx is equal to 0.005. And then f of x is equal to 2x squared. Now, this is, of course, dy is equal to dx times f of x, which is f of 4, which is, well, f prime of x, so it's going to be 4x, times, so that's going to be 16, right? 16. So I'm just going to use my calculator for this one. So 16 times 0.005, that's going to be about 0.08. That's the change. Now, let's look at the actual change. So this should be a good closer to the actual number, right? Because it's smaller. So let's see what happens. So if we look at f of x equals to 2x squared, and we have evaluated that up there, it's just equal to 32. Now f of x is now 4.005, 4.005, so x is 4.005. That's going to be multiplied, so that's going to be squared and multiplied by 2, so 4.005 squared times 2 is going to be 4.005 times 4.005 is equal to this number right here times 2 is 32.08005. So 32.08005. 0.005. Notice how this is going to be 0.08. This is going to be 0.08005. Look at that. It's just a difference of like 0.005. No, and this one, however, had a difference of 0.5. This was 0.005. So it's getting better and better of an approximation. So if we get smaller and smaller, right, as we get closer and closer, as the distance becomes smaller and smaller, if you looked at the limit as h approaches 0, this is essentially what we're doing, right? We're looking at the distance getting smaller and smaller. We're going to have a better and better approximation until we get infinitely small, and where we have exactly this right over here. Hope you found this video helpful.